Yes, good morning and welcome to today's lecture. We'll move to something different from what we did last week. Last week we finished up on uh, sequence and series. But though we'll still be able to look at some application questions and as part of our continuous assessment, just to see how far the concepts have been implemented. Okay, so as part of our continuous assessment, we'll always look forward into more questions just to help us around now. So today I want us to look at set theory as a topic. It's a very straightforward topic, but forms a very strong foundation for other topics in computer science, information technology, software engineering, and even engineering itself, electrical and other forms of engineering. So as highlighted there on the slide, that's the man behind set theory. He's a German mathematician who introduced that concept. And I've mentioned before that set theory provides a very strong foundation to other topics, including counting, including graph theory, relations, and finite state machines. Now, graph theory and counting, you might experience it going forward when you'll be doing a programming at an advanced level. You'll experience a graph theory, how it helps in network formulations, network root calculations, and so on. So it's a very important topic in information technology, computer science, and software engineering as a whole. Okay. So set theory itself is very basic and straightforward. Okay. So let's look at a definition of a set. What is this set we are talking about? It's no difference from what you know. There's no difference from the ordinary definition in English. It's not different from the geometric set you used to carry back then in class 5 or even Form 4 when you're doing your mathematics exams. Okay, so it's the same concept here. So it's a collection of objects that are clearly identified. Okay, so the objects within a set, we call them elements. So if you look at the basic example of the set that you used to carry right back or back then all those content inside the 15-centimeter ruler, the protect the pieces of rubber there. So I was saying that the elements are those objects that we find in a set. Okay, then we say that because we are classifying these elements as the objects within a set, then they have membership. That's the organization of a set. They have membership. And for easier representation, sets are represented by capital letters, while the elements are represented by lowercase letters. And this does not mean that set elements are only letters. We have numbers, we have symbols that are also part of the elements found within a set. Okay, so the basic foundation here is capital letters as used for representation or denoting set, and then the rest of the considerable items within the mathematics circle are used to represent the elements of different sets. Okay, so we have what we call symbols in set theory. We have what we call symbols in set theory. Basically, some of these things are the ones we are saying will introduce us to major topics moving forward. Okay, so we have set symbols. We're going to encounter a number of them as we move forward. But now we've talked about membership. We've talked about belonging. So these are keywords. Belongs to, is a member of, is a set, is an element of. Those are keywords in sets theory. So which symbol do we use to represent that? We use this symbol here. Okay. We use this symbol to represent that. You can call it a capital E. Okay, though it doesn't look like a capital E. Okay, but that's the symbol for element. So if you want to say Y is a member of set A, or Y belongs to A, okay, that's how we express it mathematically. Those symbols are going to be very important moving forward and moving forward in future. Okay. Now, if an element has been withdrawn from a set, it no longer ceases to be a member, meaning is no longer a member of that particular set. So how do we express that symbolically? We use the membership notation, but now with a cross or a forward slash, just to cancel the membership. So that symbol there is what we use to represent non-membership of a set element to a particular group of elements or to a particular set. So that is specifically the interpretation or definition of a set in a broader concept. Okay, definition of a set in a broader concept. So there's one for maybe your hand. There's the index, middle ring, and pinky, maybe fingers. Okay, so that might be what your hand constitute. So what you can wear within a particular day. There's a set of your today's clothing, shoes, socks, hat, pants, shirts, and so on. So that's a set of its own kind. Okay. So I mentioned previously, this is basically a group of items that can be defined. They are related in a way. Okay. So when you have elements that are not even related, that's not a set. Elements must sharing properties together. Then could amplify to be a member of a specific set. So notations, more notations and symbols, as I mentioned, we're going to come across quite a number of them. So now in set notations, first representation of the elements. The curly braces, sometimes you just call them brackets, but in programming and specifically mathematics and computer, they mean something different from what we call brackets. Okay, because we have brackets, we have parentheses, we have the curly braces, and we have square brackets. So we have more to that. So what we're using here is the curly braces. I'm sure you know them, and you've seen them on your keypad. Okay, so they're used to enclose the set elements. Then the elements themselves are but the elements themselves are defined by commas. They're separated by commas within the curly braces. Separated by commas within the curly braces. So if you have what we later call an infinite set, meaning a set that does not have a definite end, is a continuous set that does not have a definite end, then you use the three dots as the last element, meaning that particular set is continuous, no definite end. You can't be able to tell this is the last element in this set. So examples are provided there. A set of vowels and a set of positive integers less than 10. So those are conditions that define the set element. What we'll also call later the cardinality of the set. So those are examples of how we define our set. So there's that domain that we provide. So if we say positive integers less than 10, anything beyond that, odd positive integers less than 10. So anything beyond that or out of that context is not a member of that set. So more examples. So those sets, the way they are defined, with the exception of the last one, you see prime numbers, odd numbers, even numbers, the way they are defined, they are called infinite sets, meaning there's no definite end. You can't be able to count even numbers from the beginning to the end, okay? You can also not be able to do that for odd numbers as well as prime numbers, okay? You might really have trouble trying to compute that unless you have a computer program that will do that with a lot of ease. So those are just more examples of what we are trying to explain. So that's another class of sets that we say that are not well defined, meaning there are no specific conditions as to its formation. We don't know why the numbers are classified the way they have been classified. Okay, so always the classification of set elements or the formation of a set should always have some conditions attached to it. Okay, so we formulated this set because 1, 2, 3, or because we are subscribing to this type of conditions here. So those are just examples. You can pick them or write them down as we move forward if you are doing so. Yeah, so those are examples that will just challenge you whether the set is well defined or not well defined. Okay, so there are a number of tasks there that you just need to identify. Are they well defined or not? Okay, so that's just to really set up the ball rolling on more interpretation of what sets are supposed to mean. Okay, so this is what we meant by when we say member of. So that's what we meant by saying that. So if those are the sets that are provided, for instance, 1, 2, 3 is a set. Maybe we call it X or we call it W. And remember, we are supposed to be using capital letters. Then we can definitely say 3 is a member of that particular group. Okay. The same happens to number 2, -5, -1, -7. We can definitely say 1 is a member of that group. Note membership can be expressed as 4, 5, 6. 3 is not part of that. ABC, BCD is not part of that. So that is membership at NaN and non-membership, just being expressed from the collection point of view. Okay, so we've talked about the elements, we've talked about membership and so on. Now, so we say that how do we make good use of this type of sets? We normally say we have to know the elements within a set. How do we express that? The elements within a set, the number of elements within a set, is expressed as n brackets A, where A is the set in question. So you can as well have n in brackets W, or n in brackets students, or n in brackets Kenya. Okay, then you close the bracket. So that's how we express that. Now this is called cardinality of the set. Cardinality of that set. Okay, so the number of elements found in a set is expressed as n into brackets A, where A is the set in question and A can change. So if A changes to Y, then we'll have n into brackets Y. Then you count the elements within that set and then you express it. And I've said in set theory, that concept there is called cardinality of set A. Cardinality of set A. So those are different ways of representing sets. We're not going to really stress ourselves into them. They're very, very basic things. We can just have a look at them very fast. So there are 3 ways you can express sets. Okay, there are 3 ways you can express sets. Just basically, how are you going to put your set elements together? So that's the tabular form, which is actually the primary way of expressing sets. You look at most of the content about sets, then that's the method we use in expression. So that's tabular form. Descriptive form. Okay, descriptive form. So you use the words. So like, for instance, you look at set C, 1, 2, not 1, 2, 1, 3, 5, 7, 9. That's a tabular form that we had talked about. Okay, so in descriptive, you can say set C has positive odd integers. Is an infinite set because it continues. There is no definite end. Okay, so that's descriptive. Then set builder form. This is actually used now in counting principles and tree or graph theory. Okay, so you use more symbols to do that expression. So for instance, look at set A. We are saying it contains elements represented by X, where X is a member of N. Most of the time, N here will always mean natural numbers, okay? And X should be less than or equals to 5, okay? Same to B, contain elements represented by X, a member of E, and X must be less than or equals to 50 and greater than 0. Okay, so you can see the membership comes first, then the condition follows. That's how we express sets in form of what we call the set builder form. This is actually the professional way of expressing sets, especially for people in technology. That's a professional way of expressing sets. Now, the same happens to C. There's a condition there. X must be greater than 0 and should be a member of O. So we'll, if you're expressing your sets in this manner, then you will always define what N, E, and O means. If there are things that are not known to within the faculty of mathematics or within the mathematical environment, people do not know their meaning. So you have to define them. So you'll have to tell us maybe N is set of positive numbers, or N is natural numbers, maybe E a set of odd numbers, O is maybe positive numbers. Okay. So that's what we call the set builder form. So those are the three ways in which you'll always see your set expressions provided within that context. Okay. So you can try that in the set builder form. So you look at set A. Look at set A. My membership can be, look at 2, 4, 6, 8. My membership can be set of even numbers. Okay. Then my condition would be X is less than 10. Because if you say less than or equals to 10, then 10 should have been included there. So I'll say X is less than 10. And my membership is set of even numbers. So if you look at set of even numbers between 0 and 10, of course, less than 10, then you'll find 2, 4, 6, 8. I think so. You'll find 2, 4, 6, 8. Set B, you can try it on your own and tell me your membership and tell me your membership. Same to set C, D, and E. So you can try out, then just chat your response. Okay, so we can move on. Maybe you can try that at your own time and be able to see if you can be able to come up with something. Okay, so you just need to build. So maybe we can I can just mention set B and then we move to something different. So 3, 9, 27, 81. Probably probably this will need the knowledge of sequence and just see what happens there. I think is there's a common ratio of 3. Okay, there's a common ratio of 3. So 3 times 3 is 9, 9 times 3 is 27, about 27 times 3 is 81. So there's a common ratio of 3. So basically you can call it multiples of 3. You can call it multiples of 3. Okay, as your membership. Then of course your condition should be less than 100. Okay, less than 100, so that immediately you're going to multiply 81 again by 3, then you're going to go beyond 100. So your condition should restrict the movement to 100 so that you stop at 81. Okay. Yes, so you can try C, D, and E and see what you're able to come out with. Okay. Yeah, so you can see the answers there are slightly different from what I said, but they are there. So number 1 is even numbers. And of course, X is less than or equals to 8. You can as well say X is less than or equals to, not equals to, less than 10, so that you stop at 8. Okay, so B has been expressed as 3n, multiples of 3, and n is a member of a natural, n is a member of n, and n should be less than or equals to 4. So that's a different expression. Though they've not defined for us what n is, probably it's the assumption in mathematics that n means natural numbers in mathematics. Is something that is well known. But because we've done the concept of sequencing and series, you can as well bring that concept and maybe give the expression that I'd given earlier, okay, through the eye of sequence and series, where you know there's a common ratio, you know there's a common difference, and so on and so forth. And to explain it will be much shorter compared to what is being provided as the answer to question B. So you can look at question C, D, and E and express it in your own way. Then maybe you'll check the content from here, either watching the video or just looking at the notes themselves. Okay, so those are the previous questions, answers to the previous questions. Now, okay, so those are the known mathematical sets. I was mentioning n as set of natural numbers. Z is set of integers. Z plus is set of positive integers. Q is set of relational numbers. Q plus set of positive relational numbers. R set of real numbers. R plus set of positive real numbers. Then C, the set of complex numbers. So most of the time you might find sets being expressed as membership of those particular famous sets. We later call them universal sets, but no explanation is given. So basically what you need to know is that they are referring to the standard definition of those particular sets. Okay, so there's nothing new about them. So those are the famous mathematical sets of the well-known standard mathematical sets. So you can continuously refer to them. As you build your sets. Okay, as you build your sets. So more of that explained a little bit further. More of that explained a little bit further. This is not really of importance to us. We are not really studying numbers in mathematics. Okay, but now because they are type of sets, then we really need to at least grasp some few definitions about them. Okay, but that's basically the outlook of those particular sets explained in a more familiar way. So you can go and Google and check what are real numbers, what are, of course, you know what positive integers are, you know what integers are, you know what natural numbers are, okay? In real mathematics, okay, that is maybe for those guys pursuing mathematics, integers is 0 to 9. Okay, that's the definition of integers. But now you see here, we define it as all set of numbers that appear in mathematics. You can see the 3 dots from the left, the 3 dots from the right, meaning that on the left, there are so many other numbers that still exist. Equally on the right, so many other numbers also still exist. Okay, so that's what we define as integers in form of sets. But that does not need to really worry you, because you'll always be given the domain on which to align your set elements to. Okay, so those are basically more and more explanation on how sets work. Okay, so just a bit of more meaning to different symbol. I told you in set theory and programming, our interpretation of the brackets there is very, very different from how other professionals will interpret brackets there. Okay, I said we have the square brackets, we have the curly braces that we're using here, we have the parentheses. Now you can see really they have different meanings. So here we are saying it's an open interval. This one is called half open interval. Okay, and this one is called a closed interval. So you can see really how our interpretation of brackets is very, very important in set theory and programming. Okay, so I'd mentioned types of sets, finite and infinite. I think we don't need to go back there. I'd mentioned finite is one that you can count the members. Infinite is one that definitely you'll not be able to tell somebody the members of this set is 1,000. Okay, you won't be able to tell the cardinality. Cardinality of that set is uncountable. Okay, so that is when you talk about infinite set. Finite, countable. You can see the examples provided there. You can definitely be able to count and say there are 5, there are 7, there are 3, there are 2, and so on and so forth. So the cardinality is well known. So infinite, I've mentioned that quite a number of times. You can just have a look at example 1 and 2. So you can have a look at that maybe at your own time and try to comprehend the meaning and tell whether it is finite or infinite. I can definitely plug into E and say E is infinite, set of numbers which are multiple of 3. So you can see the expression there is on different forms. We have the roster form, we have the tabular form. So the way the sets have been expressed there, or the way they've been represented, they are text different forms. So that's why it was also quite important to learn the 3 different ways of representing sets, so that at any given point, you don't get lost. Which mode of representation is this? So the next type, after finite and infinite, is the empty set or the null set. And we've said the representation can either be curly braces and you leave it without anything inside, or you use this symbol here. Okay, use that symbol there. And the note is provided there just to distinguish clearly the symbols there. Okay, the two symbols mean two different things. On the left side is an empty set. On the right hand side is what we'll later call a singleton set. Okay, a singleton set. There's a different type of set. Okay, so that's why we are saying the two are not equal. That's why you see the equal sign crossed. The two are not equal. The next one is just the one we've talked about, unit set or singleton set. Is a set that contains exactly one element, and the representation is provided there. So you can use the representation of this, or you can just put the element inside there. Okay, so example there is set S contain an element in form of X, where X is a member of N. We now know N is set of natural numbers. Now, what makes it a singleton set is because of this condition. The number has to be between 7 and 9. And natural numbers, these are, we'll call them loosely whole numbers. Okay, they don't have the fractional parts. Okay, so the number that is a whole number between 7 and 8 is only 8. So that's why S qualifies to be a singleton set. Okay, so those ones you can have a look at them, just more examples for you to try your understanding of those type of sets. And of course, the answer is follows there. Then equal and equivalent sets. Now, this is normally a bit tricky. When do we say sets are equal? They have the same number of members or elements, and the elements or the members must be sharing the same property. So it's not only about numbers, but they have to be the same. Okay, so we say that the order in which they are written does not really matter, provided one, they are the same element, two, they are equal in number. So look at example 1 provided there, A and B, and C and D. Those are definitely defined as equal or equivalent sets. Okay, so for equivalent sets, we are talking about the numbers, the cardinality of the sets. We know about the cardinality of sets. How many elements are there? Then we can say those two sets are equivalent. So remember, for equal sets, they must be equivalent to, meaning the number of elements must be the same, as well as those elements must be similar. But for equivalent sets, we're just looking at the cardinality, how many elements are contained. So check F and G. So we are looking at the cardinality of F and cardinality of G. If they are the same, then we conclude that those two sets are equivalent sets. Same to A and B in example 2. Okay. So the task there, you can check them at some point. Next one is subsets. So a subset is basically a set that contains a part of the elements found in another set. Okay, so I'll basically introduce another type of set here, just to ensure that the concept of subset is brought out clearly. Subsets originate from what we call the universal set. Okay, so universal set is that set that contain all the elements that are in consideration. Okay, so like for instance, I can say n, which is natural numbers, can be a universal set. So if you pick positive integers from 1 to 10 from n, then that set that is representing those positive integers becomes a subset of n, of the natural set of numbers. Okay, so the notation is here. So this is how we indicate subset. It's kind of an inverted U and a line below it. So that means if we're going to denote not a subset of, then just cross this. The way we were crossing the membership, I hope you remember. Okay. So we say set A is a subset of B if and only if every element of A is also an element of B. So meaning B must be bigger than A for A to qualify to be a subset of B. And we say the empty set is considered a subset of every set, because it has nothing. Of course, any other set, including the universal set that I've just introduced, if everything is removed, then it has some empty set. It's an empty set. So that's basically the interpretation there. The most important thing is just ensure you get to know the symbol, because that's what we'll be using in mathematics, not the literature. Example is provided for there. Look at set A and set B. B is bigger than A in terms of cardinality, and A only picks a few elements from B. Then we can definitely say A is a subset of B. A is a subset of B. More examples, F and G. Not a subset example. I've mentioned that, how you represent that. I've mentioned how you represent that. So your task, you can have a look at them at some point just to test your knowledge. Just to test your knowledge. So you can always get the maximum number of subsets that can be drawn from a set. Okay, so you can always draw a number of subsets that you can obtain from a set. So 2 raised to power n, where n represent the number of elements that are found inside there. Okay, so if you want to know how many subsets you can pick from a set, then just count the number of elements, use it as a power on 2, and then you'll be able to get possibly the number of subsets that you can be able to compute from that given set. Another type of set is proper set. Proper subset. Basically, we are saying that there can be a situation where A is a subset of B, but they might have equal number of elements. Still, it qualifies to be a subset because it contains part of, okay? But rather, those two type of sets will qualify to be equal sets rather than a subset. So in case of a subset, then there has to be some proper relationship. So we say if A is a subset of B, then B, the cardinality of B must be greater than the cardinality of A, at least by 1. That's when we talk about proper subset. That's when we talk about proper subset. So look at example 2. A is contain 1, 2, 3 as the elements, and is considered a proper subset of B because B contain 1, 2, 3, 4. With an extra element compared to A. So in such a scenario, we can definitely say that A is a proper subset of B. The symbol changes, okay? Symbol changes, and we no longer have the line below. You saw the line below the inverted U, we no longer have it. Okay, A is a proper subset of B. Okay, so that's basically an interpretation of subset and proper subset. Subset and proper subset. Most of the time in mathematics, we'll only mention a subset. We'll not always go into whether it's proper or not. Okay? But it's good to mention, or it's good to know there's a distinct difference between a subset and a proper subset. So that's for you. That's for you, your task. So I've talked about cardinality of a set a number of times now, and I'm sure we know what it is. Okay, so basically, it is the number of items in a set. Okay. So if, as I mentioned earlier, if we are talking about infinite set, then its cardinality is uncountable, so it's infinity. Okay, I'm sure you remember this symbol in mathematics. Okay, so look at statement 3. If A is an infinite set, then its cardinality is supposed to be infinity. Remember, I also mentioned a way of representing cardinality, n brackets A, where A is the set in question. So you can as well represent them like this, the way they. So the mode of representation here will take different shapes, or will take different forms. Okay, but the representation remain the same. Okay, so what is big here is that if a set is infinite, meaning it has no definite end, its cardinality, its counting is represented as infinity. We don't know at exactly what point it will be able to stop. But for the case of our lecture, or for the case of our unit, let's represent our cardinality as n into brackets A, where A is the set in question, or n into brackets W, where W is the set in question. Okay, so let's adopt that for the case of our lecture, or for our unit. But if you meet this kind of other representation in any of the books or a set of notes, know that they really mean the same thing. Okay, so those are just examples of the cardinalities that you're presenting. Okay, so you have a look at them and be able to see how the representation is done. Keen interest, look at B, set B. So we are saying set B contain X elements, where X is an odd number divisible by 2. Okay, what is the cardinality of set B? Is 0, because really there is no odd number that is divisible by 2. 3 divided by 2, we have a remainder of 1, 5, 7. So definitely the cardinality of set B is 0. It has nothing into it. In other words, that definition for set B is similar to an empty set. Power set is another type of set. Basically, you remember saying 2n, 2 raised to power n, that's what we call power set. All the subsets that you can draw from a set. Remember, we said if you want to know how many subsets you can make out of a set, then the formula is 2 raised to power n, where n refers to the number of elements or members that are found within that particular set. So all those subsets you're going to extract from there is what we call power set. Example is provided there. So take a bit of mistype there. Take a bit of mistype there that C and D is missing on set A. So don't get confused. There's a bit of mistype there. It was supposed to be A, comma B, comma C, comma D. That's when we have 4 elements, and then we raise 2 to power 4. And then we get all those subsets that together is referred to as power set. So your task, okay, now the other example that brings on board a new application of area of sets, a new application area of sets, is what we call the disjoint sets. Okay, these are sets that do not have anything in common, no element in common. Okay, they don't meet. So the reason why I'm saying that brings into brings us into a new application of sets is the diagram you're seeing here, the two circles and the bigger rectangle. Now the two circles and the bigger rectangle, in set terms, we call it a Venn diagram. VENN, a Venn diagram. This is a symbolic, or rather a graphical representation of sets. Okay, especially the operation of sets. The operations of sets. So the circles here will represent the sets. Okay. The rectangle here will represent the universal set. Remember, I talked about that universal set, where all the elements are part of. Okay. So look at, for instance, S and T. The elements of that set is represented inside here. Okay. Then the set itself can be represented here outside the circle, or basically also inside the circle. The same is applicable for set T. The same is applicable for set T, where the elements are inside. The elements are inside. But the symbol is outside. So the symbol can be outside or inside. Now, the space that is remaining outside these two circles, the space that is remaining outside these two circles within the rectangle, will represent the elements that are within the universal set but are not found inside the two sets we are talking about. For instance, S and T. Okay, we're going to see an example of that. Okay. So the space is all about is used to represent that. So you can put all the elements that are not within T and S but are part of the universal set. So for instance, if we said our universal set is a set of natural numbers from 0 to 10. from 0 to 10. Look at set S, 2, 4, 6, 8. Set T, 1, 3, 5, 7. From 0 to 10, which numbers are missing? We are missing 0. We are missing 9. And we are missing 10. So this space outside these two circles can as well represent 9, 0, and 10. That's what I'm trying to say. Now back to the disjoint. Disjoint means they don't share anything. Look at set S and T. Really, there is no element that appears in T and appears in S. So that's why the two circles are drawn apart. We're going to see sets which are not disjoint. How do they appear in a Venn diagram? So if you have a question, you just raise your voice or you just type there. Okay, so another expression that can be used to define disjoint sets is an intersection that is empty. Now that introduces set operations. Intersection represented by, I'll call it a dome-shaped N, meaning it doesn't look like the normal N where, but now it has a dome-shaped hub here. This is called an intersection of sets. So intersection means that there's some elements that are shared in between these 2, 3, or 4 sets. Okay, so if there's nothing to be shared or there is no elements that appear from both set A and B, then we say its intersection is an empty set. What is expressed here? So for instance, if S and T are two sets, and we are told the intersection is 0, or not 0, is empty, then we say the two sets are disjoint. They don't share any element. So that's why in our previous diagram, the two circles are drawn apart. Whatever the what is called here overlap. So we say if two sets are disjoint, we can draw the two circles without any overlap. Your task, you can have a look at that at your own time. Okay, so I've introduced Venn diagram briefly. We're going to finish up on it. It's basically what I've just introduced in the previous section there. So it is diagrammatic way of representing Venn diagrams from a very renowned mathematician called John Venn. Okay, so we are saying once again the universal set had introduced it before, but in the convenience of a Venn diagram, we say that the larger set is called the universal set, and in case of symbolically, we use an E to represent it. Okay, so that's also another symbol that you can make good use of. Capital E is used to represent the universal set. Other representation letters will also come from different mathematical areas. So what you need to know is the definition. What is a universal set? So even if you are told universal set F, you know the meaning of a universal set, not really the letter that has been used to represent it. So in case of a Venn diagram, that is represented by the large rectangle. Then the other sets are represented with, by the circles inside the rectangle, just the way I had mentioned in the previous content. Okay. So just the same thing here. In fact, I think the previous one had represented it more organized compared to this one. Okay, but now what I'm adding now is that universal set, you can represent it with E or any other letter, provided you know you are representing a universal set, a rectangle representing everything within that domain. Domain is now the allowed framework, okay, or the allowed number of elements, okay. So you can see that our universal set is from 0 to 10, okay. So if we have set A, which represent 1, 7, 3, 5, 9, then meaning that the remaining elements that were part of the universal set should occupy the empty space, outside the circle. Okay, should occupy the empty space outside the circle. Moving forward, the elements 0, 6, 8, 2, 10, 4, we can represent them as not A. Okay, meaning they are elements that are not in A. Not A. We are going to see how that is represented. For computer scientists, you'll be able to see that well represented in discrete mathematics in a more broader way. So you can represent subsets from different perspectives in a Venn diagram. Look at the example provided there. If S is a subset of T, then the circle representing S is placed inside the circle representing T. Okay. Then the elements that are not part of S but are part of T can be represented outside. So if S was 0, 1, 2, and T is 0, 1, 2, 3, 4, then from our definition of a subset, S qualifies to be a proper subset of T. Therefore, in terms of Venn representation, then S is inside T. S is inside T. 201 is inside 4, 3. So in totality, T is S plus 4 and 3. Okay. Okay. So originally, if our universal set E was 0 to 10, then the note presented there, 5, 6, 7, and 5, 6, 7, 8, and 9, and 10 should be outside both the circle representing T and the circle representing S. So the empty spaces should occupy that because they are part of the universal set, but they are not found either in sets S or in subset T of the universal set. Next operation that can be represented in a Venn diagram is union of sets. A bit challenging. It is similar to addition, putting things together, but here we are really concerned of the repeating elements. So in union of sets, we combine sets of one set and the other. For instance, if A and B are sets, then the union of A and B is basically putting the elements together. So look at A. A is 1, 2, 3, 4, 5. B is 2, 4, 6. Take keen interest on how we treat the repeating elements. Okay? Take keen interest on how we treat the repeating elements. So we'll have 1, 2, 3, 4, 5, 6. The fact that 2 and 4 is appearing twice, both in A and B, we don't need to repeat them. We don't need to repeat them. Otherwise, we'll change the concept of union. It will be representing something different. Okay, so combine the elements together, but repeating elements, just write one of them, or just let them appear once. So like 2, let it be once. 4, let it be once. That's what we call the union of sets. In the Venn diagram, that's the format it will take. In the Venn diagram, that's the format it will take. In the Venn diagram, that is the format it will take. So A and B. So this is the union. 2 and 4 2 and 4 is special. It is the shared part. Remember, I mentioned that the part that is shared is called the intersection of set A and set B, the part that they share, 2 and 4. Okay? But now the union is putting everything together. But the part that is shared is called the intersection, the part that is shared. So that we don't lose the touch that 2 and 4 belong to B and 2 and 4 belong to A. Okay? So we put them in a shared region. That if you are counting elements on part A, you count them. If you are counting elements on part B as well, you count them. So examples of union described further. So look at set A and set B. The only thing they share there is 4. So it is only 4 that is going to be in the intersection point of the two circles. Where the two circles intersect, that's where the 4 is going to be, because it is only 4 that is shared between A and B. So you can check on those other more examples at a later point. More examples of what unions will provide, just to try and understand the meaning of that. Okay. Then lastly, I've mentioned it quite a number of times, but just going through it once again. Just going through it once again, the intersection. I mentioned that is the shared part. So the shared part. So look at set A and look at set B. And you can determine which elements appear in set A and appear in set B. That is what we call the intersection. That is what we call the. I hope you saw the element, the symbol that we use in representing the union. It is U, okay, kind of U. Intersection is an N, and I say they are dome-shaped, meaning the upper and the lower parts are curves. They are curve-like, okay? So in a Venn diagram, that's how intersection will look like. I think I've mentioned that quite a number of times. The shared part, the elements that appear in both the two sets, I've mentioned that a number of times. So those are two major operations in sets. How do we work with set elements? One of the things we can do with set elements is that we can be able to get the union. Another one, we can be able to get the intersection. We can be able to extract that part or represent that part of elements that repeats themselves, are present in A and are present in B. So more examples of intersection I've mentioned is just the elements that repeat themselves, or not repeat themselves, but appear in both the sets that are provided for. And how that is how we translate them into a Venn diagram. So 7, 3, 7, 13, 7, no, sorry, 1, 7, 13 are the elements that appear in set A and set B. So more examples, you can be able to look at them, just have a look at them. So if there's nothing to be shared, then the position for shared sets remain empty. If it is empty, those type of sets are disjoint sets. Your task, you can have a look at that and try and interpret based on what you've understood. The solutions are provided there. You can have a look at them. Solution is provided there. You can have a look at them. Lastly is the difference between sets. That is the last operation that you can be able to perform with sets. The difference between the sets. Now, difference here is is not the same way we do difference in ordinary mathematics. So if I say difference between sets, it's not the subtraction that many of you know in mathematics. It's something special. So look at set A and B. Set A is 0, 1, 2, 3. Set B is 2, 3. What is the difference between those two sets? Is 0 and 1. And that difference is specific. It is A minus B. Okay? It is not B minus A. So A minus B is 0, 1. That means elements that appear in set A but are not found in set B. If it was the reverse, B minus A, that set representing the difference will be empty because all that appears in B are found in A. So B minus A is an empty set. but A minus B is 0, 1. So get to know that special difference. So example provided there, A, B. So what is the difference between A and B? If A is 2, 3, 2, 1, 2, 3, and B is 4, 5, 6, then the difference between A and B is the elements that are in A that are not found in B. B and A is the elements that are in B that are not found in A. So your answers are there. Okay. So you can interpret or you can try and absorb what we've discussed today. Then I will post questions that tries to apply these concepts. Okay. On the portal, then you can try and answer them out. I also post a link to the video, and of course the video will be there maybe for today and maybe part of tomorrow before I can upload it to YouTube. And of course the link to the lecture notes too, so you can still go through them. But I'll now bring questions that you can have a look at them. Then next week we can rush through them as we check maybe the points that were not really clear. Okay. So unless there's a specific question,